What's up, guys? It's me, back with another YouTube video. You know, me, that guy who made a triangle. What was that, 2 years ago? Well, in case you don't remember me, my goal is to make the hit video game Super Mario 64 in the kids' coding website, Scratch. Probably the biggest problem with this is that Scratch only has 2 dimensions, but Mario 64 has 3. Which is why, in this video, I'm going to go through all the steps it took me to make a 3D engine, completely from scratch. I do have some experience making a 3D engine, so I won't be going in completely blind. A couple of years ago, I made a 3D renderer in Python, which is now completely broken, and there is absolutely zero chance I'm going to read through this code to figure out why. But I'm basically a professional. So how are we going to actually make a renderer that goes from a 3-dimensional world to a 2-dimensional screen? Well, it turns out there's not just one single way to make a 3D engine. If you look up 3D games on Scratch, you'll find a bunch of games that use various methods to render 3D space. This game, for example, works by sending out a bunch of rays away from the camera and then drawing lines based on where these rays intersect the wall. A game like this works by finding where a single point would be located on screen and cloning the sprite there. Instead of using triangles, games like these save a ton of computational power by only defining single points. When it comes to 3D graphics in general, as far as I understand, there are 2 main methods of 3D rendering, those being ray tracing and rasterization. In ray tracing, the camera shoots out a bunch of rays and the computer calculates where they hit objects, and render the scene based off of that. This allows for fancy things like reflections, refractions, shadows, etc. Alternatively, you can shoot rays out of a light source and diffuse them off surfaces until they hit the camera. The other method, rasterization, takes the triangle in the scene and transforms them to find where each of the vertices would be on the screen, and then draws a triangle using those transformed vertices. Rasterization also includes determining which pixels are located inside a given triangle, but in our case, Scratch does this for us when we draw the triangle to the screen. In this video, I'm going to go through everything it took for me to make this cube, and all the trials and tribulations that were forced upon me in my grueling, arduous journey. Now, there are hundreds of tutorials on how to make 3D games in Scratch, and you might be saying, oh, just follow a tutorial, it'll be so much easier. But of course, I'm going to try to make it all on my own. What am I, a coward? I don't need anybody else's help. So I'm going to walk you through what I did, starting, of course, with how But before I show you what I did wrong, we need to take a step back and look at the problem. The end goal is to take a 3-dimensional space and project it onto a 2-dimensional screen to show the player. A much simpler version of this problem is if we instead take a 2-dimensional space and project it onto a 1-dimensional screen. Simplifying to a 2D space makes it much easier to see the entire space that we're working with. This way, we can calculate the X and Y positions for each point individually and then combine them when we display the final image. Inside our space, we have a camera, which is the player, and we have the points we need to render. I'll start with only one point. So let's take a look at what I did. Here's our space. This red line shows the direction that the camera is facing, and the purple lines show the edges of what the camera can see. Let's draw a line from the camera to the point, and also the screen that we're projecting onto. Now, my idea was that we could find this angle here and compare it to the total angle that the camera can see. We'll assume that the camera's FOV is 90 degrees for simplicity. So then what is this angle? Well, since we know the location of the camera and we know the location of this point, we can construct a right triangle between them. Now, if you know some trigonometry, you can probably see where this is going. The tangent of the angle that we're looking for is equal to the opposite side over the adjacent, and we can find this angle by taking the inverse tangent of both sides. So this expression is equal to the angle that we need. All we need to do is subtract this angle from the direction the camera is facing to get it to work with every rotation. Now we can just divide by the total number of degrees the camera can see, and this is the location of the point as it's shown on the screen. So why is this so bad, you might be thinking? Well, let's rotate around a bit. When we do a full rotation, the point doesn't come back on screen, it's all the way over here. But this can be easily fixed by looping the angle so that it's always between negative 180 and 180 degrees. So now what's the problem? Let's try moving the point somewhere different. Now the point is behind the camera. It shouldn't be visible, but it is, and when we turn to face the point, it goes off screen. Take a look at these two right triangles. Since we're dividing the x position by the y position, these two triangles are considered to have the same angle. This is a problem since clearly they aren't the same triangle. To show you this, I'm going to plot every possible location of the point and the angle that gets calculated. In the green region, the angle is positive, and in the red region, the angle is negative. When the point's y position is negative, these regions are flipped from what we need them to be. We can flip them back by adding an if condition. If the point's y is greater than 0, do nothing, or multiply the angle by 1, but if the y position is less than 0, multiply the angle by -1. So now this is the expression for where our point is on the screen. It's really long, and it has an if condition. In Scratch, if statements are incredibly slow, especially if we're doing a lot of them, so it's important to have as little as possible. Doing an if check for both the x and the y of every single point for every single triangle, every frame, is going to slow down the project significantly. Many conventional programming languages have something called the atan2 function, which takes in the x and y of a point and outputs exactly what we're looking for. But unfortunately, or maybe fortunately, since there is an easier way, Scratch does not have the atan2 function, and so the only way to replicate it would be with an if condition. Arctangents are also super slow to calculate, so processing 2 arctangents for every single point, for every single triangle, every single frame would also get really slow really fast. This is the same reason I don't like whatever I did in Python, since the arccosine function is also slow. And it's broken, but, now, if I had no other options and trigonometry was the only way to project points, that would be it. It would be slow and I would just have to deal with it. But as it turns out, there is an easier way. So now, let's talk about how to... Instead of looking at the scene from top down, let's look at it from the side. We could set up 2 right triangles, one triangle from the camera to the point, and another from the camera to the screen that we're projecting onto. These 2 triangles are similar, meaning one triangle can be scaled up or down and will be exactly the same as the other. This means that the ratio of their side lengths will always be the same. We are trying to find the height of the point when it was projected onto the screen, which is this distance here. We can assume that the distance to the screen is 1 for simplicity. This means that the height of the point when projected onto the screen is just the y-coordinate of the point divided by the x-coordinate. This approach is much better than using arctangent. It only has one division operator and it doesn't require the slow and clunky arctangent and Boolean operations. Now, this works great, but it all assumes that the camera is at the origin and that the camera is facing directly forwards, which of course it won't always be. So how do we solve the problem of the camera not being in the center of the world? Let me introduce you to a technique I call shut up. Yes it is. What are you talking about? Wherever the camera is, we can just move all the points so that the camera is in the center. The camera position is just represented by numbers and code, so nothing is stopping us from just moving the points by where the camera is. In practice, this is done by subtracting the camera position from the point's position before projecting it. And for the camera rotating, we do the exact same thing. We say that the camera is facing forward, and we just rotate the world around the camera instead, which is a little bit more complicated, but it's still not too hard. In linear algebra, we have this thing called the rotation matrix. Basically, it lets you transform a point by rotating it around the origin. Here's what the code implementing it looks like. Could we have rotated the world and then used arctangent for the projection? Yes. Did I think of that? No. Am I disappointed that I didn't come up with it when I was still trying to make arctangent work? No, because then I wouldn't have looked for an easier way. Anyways, let's recap. The first thing we need to do is move all the points to 0, 0 by subtracting the camera position. Then we rotate all the points around the origin so that the camera is facing forward. Then we can use similar triangles to project our points onto the screen. And after all that, we have the y-coordinate for our point. Then we do the same projection for the x-coordinate, and we successfully have projected a bunch of 3D points onto a 2D screen. Hooray! After writing all of this out in code, this is what it looks like. And look at this! We have a cube made out of triangles that are 3-dimensional. And there you have it. But the video's not over. Look how much time is still left. Because guess what? This was the easiest part. That's right, we still have a long way to go before this thing is perfect. Let's look back at 2-dimensional triangles for a second. In my last video, I went over how I made a triangle filler. It definitely isn't perfect, and in a future video, I will likely improve it. I've been getting lots of comments on that video on how I could optimize it, and if you have any ideas, please feel free to share them, because I will be revisiting this in the future. But let's take a closer look at this triangle. I'm going to move one of the points so that it is off screen. Let's draw just the outlines to see if it makes more sense. The problem is with how Scratch moves the sprite that we are using to draw the triangle. As it turns out, you can't move the sprite off screen, meaning you can't draw a triangle that is partially off screen. If you are a very advanced Scratcher, you may already know a very easy solution to this problem. But guess who didn't know the easy solution and coded their own way of solving this problem? That's right, it's this guy. So once again, I am not yet going to show you the correct way to solve this problem. I'm going to show you how the one and only, absolute genius, random guy with no O decided to solve this problem. Here was my idea. The part of the triangle that is on screen is just a quadrilateral. You can draw a quadrilateral by just splitting it into two triangles. A triangle drawn like this would be split into a pentagon, which can be drawn with 3 triangles. And after way too much trial and error, I came across something called the Sutherland-Hodgman algorithm. The basic idea of this algorithm is that it takes in one polygon and clips it with another polygon, which is exactly what I need. I'm oversimplifying, but essentially what the Sutherland-Hodgman algorithm does is it goes through every side of the polygon you're clipping and one side of the polygon you're clipping with, and it checks whether that side needs to be clipped or not. And then it repeats this with the new polygon for every single edge. Putting this into Scratch means that every single side of the triangle gets checked with every single edge multiple times, which results in a lot of Boolean checks, which, as I said earlier, are slow. So can this algorithm be optimized in any way, or are we just forced to lose performance? Well, this implementation of the Sutherland-Hodgman algorithm was made very quickly by me, and it is very rough. A more optimized implementation of this algorithm could absolutely exist, but I'm very glad that I didn't try to make it. Because just as I finished this part, I decided to look at some other 3D games to see if I could figure out how they solve this problem. So I opened Crystal Seeker and started looking through the code. I couldn't find any algorithm for clipping triangles with edges anywhere, so I decided to look up the problem, and that's when I found the correct answer. Let's look at the default Scratch Cat sprite. When we move the cat, it won't go completely off the screen. Instead, it stops when X is 272. This X position represents the center of the sprite, which is where the pen draws from. The center of the sprite is past 240, which is the edge of the screen, so we are able to draw over the edge of the screen just a little bit. If we increase the size of the sprite to 200%, the sprite can go all the way up to X equals 320, but still not completely off screen. So it seems that the larger the sprite is, the farther past the edge we can go. But unfortunately, there is a size cap. For the cat sprite, the size cap is 540%, meaning the farthest past the edge we can go is to X equals 482. But if we make the sprite smaller in the costume editor, it increases the size cap, meaning we can go farther past the edge. So let's make a new blank costume, which does not have any size. But when we do this, there is still a size cap of 27,000, and the farthest we can go is to X equals 495. If we look at the costume editor, we can see that this supposedly blank costume is actually 2 pixels by 2 pixels, even though there is absolutely nothing in the editor. If we draw something and then delete it, now the dimensions are 0 by 0, which is exactly what we need. A 0 by 0 sprite has no size cap, which means we can set the size of the sprite to infinity, and now we can move the sprite as far off screen as we want. This means that if we have a triangle with a point off screen, we can just draw it using the old thing that I already coded, and all my research on the Sutherland-Hodgman algorithm is completely useless. But you know what? Maybe the real 3D engine was the friends we made along the way. Cool, so now our 3D engine works, even if some of the points are off screen. Yippee. But there's still one more problem we need to solve. What if the points were behind you? Let's look back at our projection math. Let's do the math for this point, behind the camera. First, we assume that the screen is 1 unit away from the camera, and then we draw our similar right triangles. We get our triangles to have a side length of 1 and a side length of -3. This means that when we set up our ratios, we calculate the point to be located at -1/3, which is the same as if the point were located here. We can see this in effect in the 3D engine when I turn around so that the cube is behind me, and it gets rendered in front of me instead. And it gets really bad if I go inside the cube, so that half of the points are in front and half of the points are behind the camera. So how do we fix this problem? I tried a lot of stuff, and I did a lot of things that I'm not too proud of. Once again, I way overcomplicated things and made more problems than I was solving. But after many ChatGPT prompts, I got the solution. Now, you might think that we can just check if the point is behind the camera, and if it is, don't draw it. But the problem is that I can't just discard the point. The point is part of a triangle, and I still need to draw the rest of the triangle. The actual correct answer is something called near plane clipping. Near plane clipping is one part of a process called frustum culling. If we look at the area that our camera can see, it is a pyramid with the camera at the tip. If we slice this pyramid with two planes, we get a shape called a frustum. The idea of frustum culling is that we only need to draw parts of the world that are inside this frustum, since the camera can't see anything outside it. This includes clipping the world with the near plane and the far plane. For simplicity, the only part of frustum culling that I am implementing is the near plane, so I won't be clipping with the sides of the frustum or with the far plane. Now, near plane clipping means that objects super close to the camera won't be rendered, which is why I spent so long looking for an alternative. But the more I thought about it, the more I noticed literally every 3D game has near plane clipping. Minecraft has near plane clipping. Roblox has near plane clipping. Unity has near plane clipping. Unreal Engine has near plane clipping. In the process of making this 3D model, I found that Blender also has near plane clipping. Even the original Mario 64 has near plane clipping, as well as far plane clipping. To explain how to implement near plane clipping, let's go back to our top-down view and have our near plane be represented by just a line. We can see which side of the near plane a given point is on by just comparing the Z position of our point to the Z position of the near plane. We do this step after moving and rotating the world so that the camera is always facing forward. Every triangle can be in one of 4 different cases, and each case is handled separately in the code. The first case is if every point of the triangle is in front of the near plane. In this case, we can just render the triangle like normal. The second case is when every point of the triangle is behind the camera, and it should not be visible at all. So in this case, we just output nothing, meaning the triangle will be discarded. The last 2 cases are when some of the points are in front of the plane and some of the points are behind. When this is the case, we can't just discard the triangle, since some of it could still be in view, but we also can't render it as is because points behind the camera are rendered incorrectly. So these are the cases where we need to clip the triangle. In case 3, we have 2 points behind the camera and 1 point in front. What we need to do is clip this triangle so that the entire thing is in front of the near plane. We can see that in this case, the resulting shape is just another triangle. We can find these 2 points where the triangles intersect with the near plane. We solve for the x and y positions separately. We take the point slope form for the sides of the triangle and set them equal to the near plane. Then, with some algebra, we can solve for this point. Then we just output this new triangle to be rendered. Here's what the code for this looks like. In the 4th case, 1 point is behind the camera and 2 points are in front. This case is slightly different, since instead of outputting a triangle, we have a quadrilateral that we need to output. We could find these 2 points using the same method as before, but this time, we'll split this quadrilateral into 2 separate triangles, and both move on to being rendered. And that's all 4 cases covered. So let's take a step back and look at our pipeline. First, we look at our list of triangles and choose one. Then we go through each point of the triangle. We move and rotate this point so that the camera is at the center of the world. Now this is where we would do our near plane clipping, but we only have 1 point. That's fine, I'll just do 3 points at once. That way we can clip the triangle when we get to this step. But now I have 9 separate variables just to describe the points. And well, I don't like how yucky it looks. So instead of looking at a single triangle at a time, let's do each step with every triangle before moving on to the next. We can make a list for the input and output positions of all the points. Now, the first thing we do is move every point in the input list to the center and add the new points to the output list. Then we can replace the input list with the output list so that our points are ready for the next function. Then we rotate all the points and add them to the output list. Doing everything step by step instead of triangle by triangle makes it easier to troubleshoot, as well as making it easier to add extra steps in the future. Now when we get to the near plane clipping step, we can take 3 points at a time, and then add the output to the output list to be rendered. This makes the last step easier, where we draw all our triangles to the screen. Because the clipping step sometimes outputs 1 try, 2 tries, or no tries, our draw function would have to account for that. But now we can just loop over every try no matter how many the previous step produces. And there you have it! We now have a project that is capable of rendering 3D scenes. But this 3D engine is different from all the other 3D renderers in Scratch. This one is special. See, this is the only 3D engine on the entire platform that was made by me. Anyways, what's up? It's me from real life. So you might be wondering, hey random guy, why did this video take 2 years to come out? Well, the answer to that question is because I have a life. And also because I spent 2 years procrastinating on Instagram Reels. That probably contributed a little bit. But we're going to say it's because I have a life. But on top of Instagram, I've spent the last 2 years doing schoolwork, playing video games, hanging out with friends, and going outside. I know, the craziest part of this video is that the guy who plays Ultra Kill and makes math videos on YouTube has been outside. But to answer the genuinely hundreds of comments I've gotten asking if I've dropped this project, no, I haven't. I've just been focused on other things. But this video's out now, which means that I can start working on the next part of the project. Well, for you the video's out, not for me, I'm still working on it. The next part of this project is going to be making the map and models for Mario 64, as well as bug fixing the triangle renderer that I made in the last video. In the process of editing this video, I tried putting together my 3D renderer and my triangle drawer to see if they would work, and they did not. It turns out there is a pretty big problem with my triangle drawer that I really thought would not be an issue, but it turns out that it absolutely is. And sometime after that, I would also like to completely rework the triangle renderer using comments that you guys have given me on that video. So if you guys have any ideas on how I could optimize or make the triangle renderer faster or better, please leave them in the comments below. I will be looking at them. But that's all I've got for you today. So I will see you in the next video in 2 years when that finally comes out. Don't worry, I'm hopefully kidding. I was hoping I would get 2 videos out this summer, but looking at the time I've got left now, I don't know how feasible that actually is. But I found that once I get into the flow of making a video, it comes out actually a lot faster than I really expect it to. So once the marching season finishes up, I'll start working on the next video during school time, and I might actually get it out before next summer. I don't know though, we'll see, no promises. You know, kind of like how I said that this video would come out 1 year ago and then I was like totally off the mark. Anyways, that's it. See ya.